Hey there! Did you know that the laws of quantum mechanics allow teleportation? That does sound cool indeed, but forget the whole beam me up Scotty thing for now and think more quantumly in terms of particles and atoms. So how is that quantum mechanics talk about teleportation and how does it works? We will give you some more details.
Yeah, thanks, Amori. Well, to dive in just a bit, as he said, we are not talking about the sci-fi teleportation. Here we are talking about quantum information and how to transport it from one place to another at any distance possible. But to do so, we need one cool property of particles described by quantum mechanics, entanglement. Basically, two entangled particles are a system where the information lies in the correlation they share. That means measuring one state is changing the whole system, and this is why we say acting on one of the particles directly affects the other.
Entanglement is described by the Bell states represented like this. They are recognizable by the fact that they can't be expressed as the tensor product of two particles. These states are key in the teleportation protocol as they are maximally entangled. Moreover, there are four orthogonal states and thus can express a basis of a two-qubit system. This basis will be very useful for the teleportation protocol and its applications.
In fact, the Bell basis is commonly used to interpret the teleportation protocol via what we call a Bell measurement. This measurement qualifies any measurement that can determine which of the four Bell states the system is in. We consider it perfect, unlike the actual experiment in linear optics that can only distinguish two of the Bell states. Indeed, we will see in theory how it is used in the teleportation protocol to optimize it when we can determine any of the four Bell states.
Now we can talk about the details of quantum teleportation. The teleportation protocol is based on a series of operations that will destroy the quantum information of a given particle at a certain point in space and recreate it at another that can be theoretically at any distance. Let's see an illustration of the protocol. The situation is as follows. Alice wishes to send a given state omega to Bob, separated by a distance and via the quantum teleportation. To do so, they share an entangled pair of qubits. We will see later why. Then, Alice performs a Bell state measurements and communicates classical information to Bob in order for him to obtain omega.
We have here the secret to untangle the two qubits shared by Alice Bob. This is why we talk about the Bell measurement. It will be put in use during the protocol. Once we have untangled the two particles, Alice and Bob are put at any given distance and the protocol can be set in motion. To do so, we will run the calculation throughout the whole protocol.
At this stage, after entanglement, the whole system can be described by an 8-dimension tensor space with a state like this one. Then, for the teleportation protocol, Alice will apply a Bell measurement on the state omega and her qubit. Indeed, we can see the four states of the basis of a two-qubit system. We can thus project those states in the Bell basis we saw before.
This is the measurement principle stating that a measurement is nothing else than a projection of the system in a given basis, the Bell basis. We have the state before and now we can replace the projection in the Bell basis as follows. What we did here magically is the entanglement of Alice qubit and the quantum state. Now the system can be determined by knowing in which Bell state Alice's system is in.
Indeed, we are at the end of the teleportation, but now is the time to use the classical communication between Alice and Bob and the final unitary transformations performed by Bob. In fact, when Alice performs a Bell measurement on her qubit and the state omega, she projects this system onto the Bell basis as we have seen. Then she will communicate the results of the measurement to Bob that will modify his qubit accordingly to obtain the information contained in omega. In the end, We can say that Bob's qubit and omega exchange roles because now it is the qubit omega and Alice that are entangled and Bob that has the information. This is why we use the Bell measurement to express the quantum teleportation as an exchange of information between Bob's qubit and omega.
Now that we have the understanding of the use of a Bell measurement, Alice will perform the measurement on the entangled system she has now. She will then communicate the results to Bob through classical communication. Thus, if she obtains Phi plus, Bob already has the quantum state. So he will perform an identity transformation. Phi minus Bob will apply Z gate. Psi plus X and finally Psi minus X and then Z to obtain the quantum state omega.
As you can see, in the end, Bob has the quantum state originally at Alice's position. Moreover, in the Bell description of the phenomenon, we can conclude that the information contained in Bob's qubit and the quantum state have been swapped. We now have teleported information thanks to the properties of quantum mechanics about measurement and entanglement.